Now coming here, sorry I missed it. So I'm GK Builder, Dhananjay Pai. So the suggested fix here is that this could potentially allow manipulation of state root chains in certain scenarios. How will it happen? So if we have a current state commit hasher and we just use the hash left right, then he could manipulate this hash left right because it is an inbuilt library, and we are just pointing the current state root and the current state salt. If you find it, like if I go up, this is an input and I'm just mapping it to it. And if you find this is again an input which I'm just mapping, and I'm not doing anything here. I'm just like the current state commitment. If you just try to find it, everything about finding where is it defined, how is it used. So it's again a signal input. So it is not very secure because you can make changes and manipulations to the state commit tree. Now the idea here is to use Pedersen's commitment, which is a secure commitment. Now you, instead of using hash left right in like just hash the left and right component, you use a secure commitment library. You just import it here, template, and then you like basically then again do the same mapping from the inputs, and then you have a padding giving you an additional layer of security. This one is basically telling you to handle zero values, so doesn't handle any. If you look, this one is the previous code, and this is my current code. So the previous value doesn't handle like for zero values properly if you look at it closely. And now like there are two components though for this. So let's zero. There are two components and we've just defined one component. It is better to handle via zero value, because if we don't handle it, like it is obviously better, but it can be considered as an ignorable or a minor bug. But at the end of the day, it is a bug. Coming to the last but not the least, where is it? Have I like, okay, this one. So the suggested fix here is range checks. Uh, the range checks for the votes is implemented using a quadratic formula. Like if you like, where is there a before? Yeah, this one is the before code, and this one is the after code. If you look at it, let me just go here. Okay, verify the option roots and this one. So the previous code, what it did was use a quadratic formula that could overflow. As I told you, it is all a finite circuit field. The max Schwarz constants, where if you look at this, the max Schwarz constant, which is in itself a very large number, and when multiplying with itself, if you see somewhere over here, it is being added to words, which means like this is a large computation to do, because words of I comma j is we are iterating to I and j, and then we are adding the max words, which is a large number in itself being added with a large number again, could obviously be have an like an overflow from the finite circuit and give you like buffer errors while compiling this circuit. So the potential overflow in the field arithmetic could like lead to incorrect vote telling. So what you could uh, face is your voters tell it wrongly. So again, it's a critical vulnerability. Malicious users could exploit this because they could create a overflow error on your circuit while compiling it or while generating the proof, second proof. Circuit constraints might fall unexpectedly. So what we do is like we can handle this like very smartly. So we just have to have a component which is a very limited field, number of vote options with the batch size. Initially, we didn't have this batch size option. We just took the number of voting options. Now we have a very finite 2D matrix storing like a 2D array or something, we can say, in this circuit. Now we just add it before you, like it was getting multiplied. We just add this, and these are again, we cannot change this value as of now because I haven't like gone through the in-depth working of this entire code. But we can say we can add this like and like make it in a confinite field by just adding this batch size here, and then again have a check on the range of the values of vote range, and then give them the inputs for both of the components, the 0th index and the 1th index, and the max votes is assigned to the 1th index. This is kept the same. So yeah, this was what I found the errors mostly were of like handling range checks and stuff like that, which are considered to be minor to middle, like in middle, and some of them like re-randomize, like handling two components, uh, but just handling a single component is a critical vulnerability that I think. And the fix here is to actually like compare and capture both the two components like on the 0th index and the 1th index for both the two signal inputs. Yeah, thank you.